Alright, 4.2 logarithmic functions. So here we're going to look at the inverse function of our exponential function that we looked at in 4.1. So the definition of a logarithmic function is that no horizontal line can be drawn that intersects the graph of an exponential function at more than one point. This means that the exponential function is 1-to-1 and has an inverse. The inverse function of the exponential function with base b is called the logarithmic function with base b. So for x is greater than 0 and b not equal to 1, y equals log base b of x is equal to b to the y power equals x. For the function f of x equals log base b of x is the logarithmic function with base b. So the equations y equals log base b of x and b to the y power equals x are different ways of expressing the same thing. So these two expressions are the same. So the first equation is in logarithmic form, so we have a log, that's the easiest way to remember it. And the second equivalent equation is in exponential form, so easiest way to remember it, you have an exponent. So for the location of the base in the exponent in exponential and logarithmic form, so when we look at y equals log base b of x, the b is our base, okay, and then the y is our exponent. Okay, so if we look at transitioning this to exponential form, we have b to the y power equals x. So again, we have the same thing. The b is our base, and the y is our exponent. Okay. The easiest way to remember this, and this is the way I was taught this, is loop and swoop. So you loop the base, and you swoop it to the other side, and that pushes the y value up into the exponent. Okay, if you have to go backwards, you loop the base and you push it to the other side. Okay, so either way, using that idea of loop and swoop will let you go back and forth between these two functions. Okay, so if we look at some examples of rewriting these into the different forms. So first, if we want to write each equation in its equivalent exponential form, so we're looking, okay, what is the base? So we have 2 equals log base 5 of x, and that's going to loop and swoop to the other side. So we have 5 to the second power equals x. And that's your answer. You don't need to simplify unless it says to, and in your homework it's going to say leave it unsimplified. Okay. So same thing with b. We have 3 equals log base b of 64. So we're going to loop and swoop the base to the other side. So we have b to the third power equals 64. And then c, log base 3 of 7 equals y. So loop our base, swoop it to the other side. So 7 equals 3 to the y power. Okay, so going from exponential to logarithmic form, the key thing is still finding that base. So on A, we have 12 squared equals x. So we take the base of our exponent in power, and we're going to move it to the other side. So we're left with 2 equals log base 12 of x. And that's your simplified form. So looking at b, we have b cubed equals 8. So we're taking the base, which is our b, moving it to the other side. So 3 equals log base b of 8. And then c, we have e to the y power equals 9. So remember, e is that logarithmic or exponential form So if we loop and swoop this to the other side, we have y equals log base e to the 9th. Okay, and log base e, which we're going to talk about this later, has its own expression. We can rewrite this as y equals the natural log of 9. Okay, so these two things are the same. It depends if it wants you to write it in terms of log or in terms of the natural log. Alright, so remembering that logarithms are exponents makes it possible to evaluate logarithms by inspection. The logarithm of x with base b, log base b of x, is the exponent to which b must be raised to get x. So for example, if we want to evaluate log base 2 of 32, we ask 2 to what power gives us 32. So one way to think about this, if you write this out, we want to simplify this to some value. I'm going to say it equals x. We can loop and swoop. So we have 32 equals 2 to some power. And then it's just a matter of plugging it into your calculator. Okay, so like 2 to the first equals 2. 2 squared equals 4. 2 cubed equals 8. 2 to the 4th equals 16. 2 to the 5th equals 32. Well, 32 is the number we were looking for. So that means our x value is our exponent. So x equals 5. Okay, so that's one method that we're going to use to simplify and evaluate logarithms. Okay, whoops. Alright, so on A, we have log base 2 of 16. So we're saying 2 to what power equals 16. From that previous page, we just saw that 2 to the 4th power equals 16. So x equals 4. So B, log base 7 of 1 over 49. So 7 to what power equals 1 over 49. So, a couple things to think about. Remember, when we're looking at exponents, negatives make fractions. So we know our x value is going to be negative. So now we're looking at 49 to what power, 7 to what power is 49? And that would be 7 squared. So x equals negative 2. Okay, looking at C, log base 36 of 6. So 36 to what power equals 6. So this is one that is tricky but easy once you figure it out. Okay, so whenever we're going from a large base to a small solution, you're going to be doing some type of root. So whether that be square root, cube root. Okay, so we know that the square root of 36 equals 6. Well, the square root is the same as what exponent? Okay, and that would be 36 to the 1/2 power equals 6. So that tells us x equals 1/2. And then D, log base 2 of the 5th root of 2. So we have 2 to what power equals the 5th root of 2. So I'm going to rewrite this so that they're both in exponential form. So 2 to the x power equals 2 to the 1/5 power. Since our bases are the same, that tells us that x has to equal 1/5. So that is actually a rule that we're going to look at when we start solving logarithmic functions in 4.4. So in a couple of weeks. Alright, so with logarithms, we also have a few properties. We're going to talk about the first 3 today. So first we have our basic logarithmic properties involving 1. So log base b of b, this is going to equal 1, because 1 is the exponent to which b must be raised to obtain b, meaning b to the first power equals b. Our other main rule, log base b of 1 equals 0, because 0 is the exponent to which b must be raised to obtain 1, or b to the 0 power equals 1. Okay, then we have our inverse properties of logarithms. So for b greater than 0 and b not equaling to 1, log base b of b to the x power equals x, and b to the log base b of x equals x. So the easiest way for me to remember these is that these almost seem to cancel each other out, and you're just left with that variable. So if we apply those in evaluating our logarithms, log base 7 of 7, so whenever these two numbers are the same, that just tells us it's 1. Because if you need to rewrite it, 7 to the x power equals 7, which means it would have to be 1. Log base 5 of 1, if you need to rewrite it, we have 5 to what power equals 1, which tells us 0. On C, we have log base 7 of 7 to the 8th power. If you rewrite that, you would have 7 to the x power equals 7 to the 8th. Like bases cancel, so that means our answer is just 8. And then this one, again, these are going to just cancel, and so we're just left with 17. All right, so now if we start looking at our graphs. Okay, so again, just like with our exponential functions, when we look at our logarithmic functions, pretend that says logarithmic right there, we have 5 basic properties. So the first one is that our domain is from 0 to infinity, and our range is from negative infinity to positive infinity. Okay, so notice those are the inverse of our y equals b to the x power. So what we looked at last class, or last time. Second one we have is that the graph of f of x equals log base b of x passes through the point 1, 0, because f of 1 equals log base b of 1, which we just talked about, log of 1 will always equal 0. Okay, so that tells us that there is an x-intercept at 1, but we can say that there is no y-intercept. And we'll talk about y here in a few seconds. Okay, third property says that if b is greater than 1, the graph is increasing. And here that's going to look like something like this. And then if 0 is less than b, which is less than 1, the graph is decreasing. And this is going to look something like that. All right, and our fifth property says that the graph of log base b of x approaches but does not pass, or how about saying it does not touch the y-axis. Which is a vertical asymptote. At x equals 0. Okay, so just like with our exponential functions and any function we've looked at this year, the graphs of logarithmic functions can be translated vertically or horizontally. They can be reflected, stretched, or shrunk. If a logarithmic function is translated left or to the right, both the x-intercept and the vertical asymptote are shifted by the amount of the horizontal shift. Okay. So, knowing that, we can look at these first two graphs. So they're kind of going to go together. So we're going to look at what the parent function looks like and then a translation. So looking at A, we have f of x equals log base 2 of x. So there's two ways you can look at this. You can leave it in the way it is, or you can transform it and say 2 to the y power equals x. Okay, because we know f of x is the same thing as y. The thing that's tricky about this is that we're going to kind of, instead of, we normally plug in our x values and solve for y, but here it's actually easier to plug in y. Okay, so our easiest values to plug in, -1, 0, and 1. So 2 to the negative first power is 1/2. 2 to the 0 power is 1. And 2 to the first power is 2. Okay. We also talked in our properties up above that we have a vertical asymptote on our y-axis, x equals 0. And then we can plot our points. So we have 1/2, -1. We have 1, 0, which shows us our x-intercept. And then we have the ordered pair 2, 1. And that gives us our function that is increasing. And there's our f of x. So looking at B, we can say g of x equals log base 2 of x plus 3 plus 4. So knowing that we have this general shape from part A, we can take that graph and we can shift it. So our translations say that we would move to the left 3 and then up 4. So with that, that means that our vertical axis is going to move to the left 3. I'm going to move our dashed line over. Okay. And then we're going to move our points left 3 and up 4. So I'm going to start with our x-intercept because that's the easiest. So that started at 1, 0. We're going to go to the left 3 and up 4. And put that point. Okay, we had the ordered pair 2, 1. So I'm going to take that and move it left 3 and up 4. And then we had the ordered pair 1/2, -1. So that's going to go left 3 and up 4. And we have that same basic curved shape that we did before. and there's g of x. So same general shape, just shifting our graph left and right. All right. So with that graph, because of that asymptote and never being able to cross it, we're never going to get a negative value for our logs. So from that allows us to be able to restrict our domain of a logarithmic function. So what we're going to do is we're going to always take this numerator, or not numerator, sorry, the value inside the parentheses, and we're going to just say that it has to be greater than 0. So if x plus 3 has to be greater than 0, that tells us that x is greater than negative 3. So our domain is going to be parenthesis negative 3 to infinity. Okay. And then same thing, f of x equals ln of 4 minus x. So ln is our natural log. This is when we have a log base e. Okay. But it doesn't change anything. Our rule still applies. So we're going to take our inside, 4 minus x, and say it has to be greater than 0. So if we solve, we add the x to the other side. We have 4 is greater than x, which means x is less than 4. So our domain is negative infinity to positive 4. And again, we're going to use a parenthesis because we can't equal 0. And there's your domain. Okay, so we have two different types of logarithms, and I'm realizing I think we don't actually have the natural log in these notes that I cut. So the common logarithm is when we have base 10. So this is the one that you're going to see in your calculator. So it's the easiest one to evaluate. And then our natural log is also easy to evaluate, and I'll show you how to access that here in a bit. Okay, so we can look at this log of 1,000. We know that that means log base 10 of 1,000. So if we want to evaluate that, set it equal to x. So we have loop and swoop, 1,000 equals 10 to what power? Easiest way to do tens is based off how many zeros are there. There's 3. So that means x equals 3. Okay, but what if you didn't know that? Okay, so if you look at your calculator, and give me 1 second. Okay, sorry about that. Okay, so if you look at your calculator, and we talked about e the last time being with your ln, but we're looking at log, that's just to the left of 7. So if we want to find log of that 1,000, just make sure you're closing your parentheses and enter, and we get the answer 3. Okay, if we look at the next problem, we have log of 5/2. So make sure that 5 divided by 2 is inside the parentheses with your log, and hit enter, and we get a decimal. And that's what you're normally going to get when we're evaluating logarithms. So most of the time it will say round to the nearest 4 decimal places. So here your answer would be 0.3979. Looking at part C, we have log of 5 divided by log of 2. So here's where you really need to be careful. So we have log of 5, and it automatically opens the parentheses. So you want to make sure you either close them or get out of the parentheses before you divide by log of 2. And that gives you the answer, 2.3219. Okay, if you're struggling with getting that correct, make sure that you are sending me an email so I can help you or attend an office hour. Alright, in D, we have log of -3. And here we get does not exist. because remember, our inside value of a log has to be greater than 0, meaning it can't be negative. So log of a negative number does not exist, and when we start solving equations, we're going to use that to help us eliminate any values. Kind of like when we looked at solving rationals and figuring out what value makes our denominator 0. All right, so switching back to notes, we have one last problem here. So the percentage of adult height attained by a boy who is x years old can be modeled by the function f of x equals 29 plus 48.8 log of x plus 1, where x represents the boy's age from 5 to 15, and f of x represents the percentage of his adult height. Approximately what percentage of his adult height has a boy attained at age 8? So age 8, that means we're finding f of 8. 29 plus 48.8 log and 8 plus 1, which is 9. And then it's just a matter of plugging it into the calculator. So I'm going to jump back to that other screen. So we have 29, 29 plus 48.8 log of 9. So our solution would be 75.6%. Let's go ahead and round that to the nearest whole, and we get 76%. Okay. The one thing that our notes are missing here, so we had the common logarithm, which was base 10, and it just looked like log of x. Okay, and that just is an understood base 10 when there is nothing written. The other one we're going to see, and we'll talk a little bit more in 4.3, is our natural logarithm. And this is when we have base e. And so normally we would write that log base e of x, but as I mentioned earlier, we can rewrite that as the natural log of x. Okay, a lot of times when you see that natural log, it's going to be cursive L, so it doesn't look like a 1, because you don't want it to look like this, because a lot of times it's hard to read. Okay, so you'll see a couple of those in your homework, but they have the same properties as any other log that we have.